Hi, my name is Leandra Brinkerhoff, and today we're going to be talking about voltage standing wave ratios, more oftenly used in antennas and radio frequencies. Voltage standing wave ratios are often abbreviated as VSWR, pronounced VSWR, which is how I'll be referring to our subject in today's video. VSWR is determined by the voltage measured along a transmission line leading up to an antenna. To understand VSWR, we first need to understand what a standing wave is. A standing wave represents the power transmitted along a line and is not accepted by the load or antenna and is therefore reflected back along a transmission line. Here's an example to better understand a standing wave. As this radio transmits a signal to this antenna, lots of times when the power is reflected back, you would think it creates a wave looking like this, with two waves, one being the forward wave and one being the reflected wave. But instead, what happens is these waves combine to create one standing wave that looks like this. VSWR is the ratio of the peak amplitude of a standing wave to the minimum amplitude of a standing wave. So as I was saying, VSWR can be determined by the peak amplitude divided by the minimum amplitude along a standing wave, or Vmax divided by Vmin. In more mathematical terms, this would mean that VSWR equals 1 plus the absolute value of gamma divided by 1 minus the absolute value of gamma, where gamma represents the reflection coefficient. Now the reflection coefficient would represent the power that was not accepted by the load being resent back along that transmission line, creating a standing wave. In terms of VSWR, a number of 1 is the lowest VSWR you can have, and this is the most ideal VSWR that you can have. A VSWR of 1 means that all of the power is being received by the antenna and none is being reflected back. So why is voltage standing wave ratio important? If we have a VSWR close to our ideal number of 1, that would mean that no power would be reflected back to the radio, meaning our antenna would be receiving all of its intended signal. But as we stray away from a perfect VSWR, we start to have power not being accepted here by the antenna that begins to be reflected back along the transmission line to the radio. Problems start to arise here because radios have trouble transmitting correct bits when an antenna is poorly matched. This can be numerically defined in terms of error vector magnitude, also known as EVM. Another problem is that when power is received back along this transmission line to the radio, it can damage the radio as high frequencies can't be processed, which then causes our original message to not be able to be transferable to our antenna anymore. While a low VSWR close to the number of 1 does indicate that our transmission line is well matched with our antenna, VSWR alone is not enough information to be able to determine if our antenna is functioning properly. The physical health and other factors would have to be considered to be able to tell if our antenna is functioning properly. VSWR simply measures if our transmission line and our antenna are well matched and that our signal is being received or reflected.